Peter's reporting the video's not working. I'll ask him what he means Facebook over there.
I'm low on mercy inside. Show me the secrets I plead.
Okay, yeah, that's probably it.
Just put the weight of the world on me, 'cause I got the will to believe. And I'm looking for mercy. Have you seen her? With diamonds in the sky. It's sweet, the days will never die. So come and fade into the sun. Let me believe that I am the can't see the future, I'm walking backwards. There's no dead ends if you fly. I ain't looking for nothing, but have you seen her? With diamonds in the sky. Between the days we'll never die.
All right, welcome back to Solid Ground. We have maybe three administrative announcements. One in the continued, let's see if we can get Scott in trouble, series of questions that Katie so kindly advanced for us. We had the next one that we were going to do was homosexuality and gender issues, which we can and still will do here, but out of serendipity or whatever, this is something that Reston Bible is sponsoring and reached out to me, the elders did, and said, hey, this is going on in the end of March. Do you mind if we basically cancel Solid Ground on that Sunday for two reasons? One, they need the space here because they're going to break down the wall and use this for overflow for the event in the event that it's as popular as they figure it might be, or at least as controversial as it might be, because this, as I understand it, I have not watched this video, but as I understand Aaron's description of this one, Dr. Yon was a former homosexual who became a Christian and subsequently adopted a Christian viewpoint on all this. I'll leave it to him to explain it all himself, but I imagine many of the issues that, or at least some of the issues that we were going to raise in class will be raised in this particular deal. And I think he's got some material on YouTube, so you can check him out as well. This webpage is on Reston Bible's website, our website, and it is at restonbible.org/event/holy sexuality, all one word. So that will at least, probably, if nothing else, it would act as a launching platform for us to have our discussion as well. So unless the class objects, since the elders have asked, I'll cancel for that Sunday. If you're interested in this, go and watch this. And then the following Sunday, we'll begin our series on this, and that way we'll have kind of at least a launching point that will be of some interest to everyone. And if what he says is really, really good, then maybe there won't be many questions. If what he says is highly controversial, then we can really wade into it when we get in here.
Is this one of those critical events that's supposed to happen at the beginning of this? I mean, we've already had one of them. Last year they were saying, mark your calendar ahead for 3 critical events that are going to happen.
I have apparently not been paying enough attention. I don't know. I don't know if it's one of those 3. Sorry, but I can ask that question. I'll ask him and see if that's what it is. It seems like this one, I don't know. Let me ask that question. Secondly, some organic from the class stuff that's happened. I had imagined that this was coming for a while. We've done a little bit of it in the past, but there's been a renewed interest in asking about having a dialogue, not a debate, not a formal, all right, you get 5 minutes and then we get 5 minutes, whatever, but the dialogues, which are becoming more popular forms of debate nowadays, I think. And they still need to be moderated, otherwise, somebody can just kind of take over. But a dialogue between Reformed tradition, Protestant believers, and we'll just say non-Reformed, basically Calvinism and other than Calvinism viewpoints. And so more people have been asking for it, and it appears that there are a few folks who might even want to sit on the panel. So it may be I and Peter versus like 5 other guys, and we're going to even ask a couple of the elders of the church who we know come from fairly strong Reformed traditions to sit in on it, and if they've got the time and space to do so. But it's something that I think is at least worth the examining. As you know, in Solid Ground, we tend to focus on theistic thought generally, and then Christian thought most broadly, and we try to hold at that level, because the doctrinal debates that happen within Christendom are good, but there are many other places to do that, and we're trying to stay at the how do you engage with the rest of the world and with your own thoughts on all these things. But I will certainly recognize that once you are in a Christian worldview, that doesn't end your logical problems. The doctrine, the kind of stuff that we talked about when we, nope, okay, I guess I'm messing up our own diagram here. But the stuff we talked about when we were talking about asystematic theology, the tiles, so to speak, when we did the tiles thing, it is the case that both externally to the rest of the world and then internally to your own mind, it must be that you have a consistent theological system. And so really, my interest in Calvinism, or as I think all Calvinists believe that Arminianism is the only other viewpoint, but Calvinism, Arminianism, Counter-Reformation thinking, Molinism, all these other theologies or theological systems or portions of theological systems, they do have to fit together in some way. And if they don't, then you don't have a consistent system. If you don't have a consistent system, then you don't have a true system. So if I'm interested in the debate solely for the reasons of I believe Christians ought to be consistent in their thinking. Be a Calvinist if you can be consistent in your thinking. Be an Arminian if you can be consistent in your thinking. Be a Molinist if you can be consistent in your thinking. But at least getting those issues out and letting people see and wrestle with that, to me, is worth the investment. If you agree then I'll maybe put something out on Facebook that says, would you like us to do this in class? And if there's not enough interest in here, then we may do it as a separate event or something like that. So it'll either be a 1 or 2 / 4 or 5 week series, or it will be an event. But if the homosexuality and gender issues thing happens at the end of March, and we happen to finish this creation, evolution, young earth, older stuff in the next couple weeks or whatever, that would give us some space in the schedule to do that possibly, and then do the next one. If not, if we don't want to do that, let us know on either after class or on Facebook, and we'll switch to the next most popular topic, which I forget what it is, but I'll put it out there as well. So hopefully that wasn't too confusing of a decision matrix. Without further ado, then let's get back to the topic at hand, which was us talking about creation, evolution, young earth and old, and anything in that general vein. We spoke a little bit about it last couple of weeks, and gave at least some hermeneutics for framing the why do we do this and why is it important and what does it mean to us side. But it was a lot of transmission on my part, so let me go into receive mode and let's ask whatever questions, make whatever comments. Now's the time to say whatever it is you've wanted to say, and I've been talking too much for it. Al, go ahead.
There's something I need to mention. You mentioned Gerald Schroeder's,
I-
what he was talking about, and I have somebody else named Russell Humphreys.
Okay.
He had a book in 1994 called Starlight in Time.
Yes.
The difference with his explanation or theory or whatever the difference with him is his doesn't rely on Big Bang cosmology, and it also gets rid of the need for the fudge factors of dark matter and dark energy. You don't need them. So
Do you remember enough about it you can summarize his viewpoint?
yeah, instead of having a Big Bang,
Oops.
put everything into existence. In his view, God could put all the stars in the universe, and there's
Like basically put them in some proximity and then stretch them out, and you didn't. Yeah. Okay. Yeah. Yeah.
and so that would be the and with that because of the theory of relativity, the light would be able to make it to Earth.
So if you're not, if I understand what Al's saying, and if Al understands what Humphreys is saying, and I'm not messing up what I'm saying, then basically, you might as well, yeah, right. So, in the 0.5% chance that this is right, here's a model, or maybe I can just say it this way. Here's a way that sounds roughly like that. That is a way of thinking that is scientifically possible. You might say it's more physically and metaphysically extravagant than some of the solutions that we see out there today, but that doesn't mean it wasn't the way that it was done. So basically, you'll remember when you've probably heard this either on a popular level or in one of your school classes or something, when people talk about Einstein's general theory of relativity, and they try to explain something like, there's a knot and there's the bottom of the balloon. So it's a balloon that's getting blown up, and they're trying to explain how kind of non-Euclidean surfaces work under expansion. And so they say, imagine you've glued a bunch of buttons to a balloon, and you can see how close they are together. And then as you inflate the balloon, the buttons, same buttons, but they're basically, I probably made them a little too big here, but they're basically further apart. And this is the idea behind the expansion of a two-dimensional surface, the two-dimensional surface being the surface of the balloon. And what we mean by 2 dimensions there is, if you're stuck to the surface of the balloon, you can only move in 2 dimensions, if you're stuck to the surface of the balloon. And then what they'll turn around and say is this is a 2D analog for 3D space. So you can't think about this in 3D space, our brains won't do it, but this is the best way 2D to think about that. Now, if you ignore that there are problems with that kind of suspension of disbelief, which I think we too often do, but if you do, that's a good explanation of of how to think on a Euclidean surface. It's also the reason why, like, you know, on the globe, if you say I'm flying from Washington, D.C. to Beijing, China, the route for that ends up going over the Arctic Circle. You know, why does it do that? Well, the answer is the shortest path might be this way instead of all around the longer equatorial route or something like that. And so these great circle routes is what they call them in navigation, occur because when you look at a sphere and you treat it like not like the airplane is stuck to the surface, but the airplane's stuck within, you know, 40,000 feet of the surface, then that's the shortest route. So, all right, why is this important? If you can do this with space, if this is the way space works, then the Big Bang is simply everything was really, really close together, and as it expands and ever expanding, you know, radius from its original singularity point, then stuff that was at this left side, kind of so to speak, of the Big Bang singularity of all of the known universe, is some distance from this stuff right here. And as it got bigger, that distance, of course, simply by dint of the expansion of the universe, these spots are getting further and further and further apart, to the point that as the expansion gets really, really, really fast, it may be the case that something over here, even if you go driving in this direction at the speed of light or near the speed of light, you can never make it to this point over here because space is expanding so rapidly in between. And the more space there is in between, the faster that total expansion is relative to those 2 points. That's probably too complicated, not a good way to say it. But the point is, the Big Bang model puts distance between things, and what it means is, like, let's pretend, for the sake of it, this is not what most folks who think Big Bang model think, but let's pretend that this is where we are, or maybe make them happier. Let's pretend that in this big circle that is the observable universe, here's stuff on the edge, here's us over here, and here's something closer. All right, so this stuff is expanding at some speed, and this expansion, if you kind of made a vector for it, you can imagine that arrow, that vector arrow, would be bigger. What that means is Doppler effect. You know, the ambulance or police car goes driving by you, you hear it high-pitched, and you hear it go low-pitched past you, exactly. So this is all low-pitched because it's going away from us. This is all ambulance going away from us. And these wave crests are going to be so far apart of the light that's emitted from a star of a certain color and blah, blah, blah. So when they hit us, they look like this. These wave crests, because the ambulance is going faster, are going to be further apart. And so what ends up happening here is, let's pretend they're the same color star, same frequency that they're emitting in. And we have ways of making really, really good guesses as to what those are in those spots. You would see this way more red-shifted, way more lower pitch on the ambulance sound scale than you would this. And we attribute that to the expansion of space. So in Big Bang cosmology, this is how we know how far stuff is away from us. A point similar to what Al's making, if it's not the point that Al and Humphreys are making, is this. You could, if you wanted to, stick the Earth here in the middle. Here's a model where this exact same principle is brought to bear. Here's the Earth in the middle of the universe, or some point, wherever you want it. And you stack the stars fairly close to each other, close enough to each other that they're, and galaxies, fairly close to each other, not so close that they tear each other apart through gravitational forces, but let's say you stack them fairly close together in like a miniature model, so to speak, of what the universe looks like now. Now, you couldn't actually do this, so I'll tell you how you could do it in a second. And then you take the outer shell and you expand it, and the next one, and the next one, and you could do this all at the same time, or you could do it progressively. And now, because as you're moving it back, it's emitting light, that light's getting red-shifted as it moves back, but it's still able to be received here at the Earth. All right, so this is a way to solve the time-distance problem of light, is by that God personally controlled the expansion of space in a certain way that the universe looks like it does. All right, so that's a way to do this. Now, you couldn't actually do this because you can't get a galaxy in that close a proximity to another galaxy without them ripping each other apart. So it would almost need to be like create outer shell, expand, create outer shell, expand, create outer shell, expand. But if you can do that at whatever rate you want, relative to the expansion of space, you could build a universe that looks like this by this method. Some people will say there's some problems with this, Other people say there's some solutions to this. But what I point out is at least the baseline principle of it is just another expansion of space way of looking at business. So I'll check the Humphrey stuff out. I don't know that I'm familiar with it. I don't think I've heard of it before, but thank you, Al. Something else to look at. Anything else you wanted to follow up with on that?
That's all I was going to.
Okay. Very good. Now, just an interesting side note, something that I would like to throw out for surely because I'm sitting here at the podium and there's an expectation that I can do this. This model of the universe here, here's your Euclidean space. It's expanding. The buttons are getting further apart. That only works if space is curved. All right, so if the balloon, think of it this way, if the balloon ain't flat, then it's not, I'm sorry, there's an assumption that goes in on here, which is this. If you say, where's the center of the universe? In a universe that's like a balloon, where all the galaxies are like buttons on it, and you say, which one of these buttons is at the center? Well, the answer is none of them are at the center, because you could pick this one right here and say, well, this one's moving away at this rate, and this one's moving away at this rate. But you could also pick this one, and all the other ones are moving away at the same rate. And you could pick this one, and you see you can't pick any one and say it's at the middle. That only works on what they call a non-Euclidean surface, which non-Euclidean is just a fancy schmancy way of saying, remember how you learned geometry in high school of like, there's a lot, these are lines, and then these are planes, and the plane is flat, and you've got two lines that are, that go in exactly the same direction. They're parallel, they'll never meet, that kind of thing. Those are all, that's Euclidean geometry. And then if you bend that space, those Euclidean rules don't stay anymore. So like parallel lines on the Earth, the parallel lines of latitude on the Earth, they do meet. Where do they meet? North Pole, South Pole, right? So non-Euclidean surfaces, different rules a little bit. They all follow from each other, but you get the point. This all assumes, so when people say things like, well, the universe is, there's no center to the universe is just expanding. If and only if the universe is non-Euclidean in its geometry. If and only if it is either curved like a balloon or what they call open, which is kind of this weird saddle-like opposite of a balloon when they talk about it in 2 dimensions, but don't worry about it. Think about the balloon for now. When all the empirical evidence, though, that we have, do you know what it says? The shape of space of the universe is between open, closed, and flat? It is flat. Yeah, so to Jack's point that he's making, you know, a closed universe is like a sphere, and so a triangle on that universe would kind of look like this. A flat, oh wow, that wasn't good. A flat universe is one that's basically a Euclidean plane, so you expect a triangle to look like a triangle. And an open one is this, like, think of a saddle. Well, I'm not going to draw this right at all, but you know what it is basically. Think of a, you know, something kind of like a saddle. Someone didn't spend any time in art school. And then triangles on this one would look differently. And what we mean by that is in this kind of space right here, the 3 angles of a triangle add up to 90 degrees. In an open universe, 3 angles of a triangle add up to more than 90 degrees. So think about the Earth itself. Think about a globe. If you went to the equator and to the prime meridian, all right, so you're going to shoot up through Greenwich, and you're going to be on the equator, and you run that all the way up to the North Pole, and then you make a 90-degree left turn at the North Pole, and you run all the way back down to the equator, and you make another 90-degree left turn, and you run along the equator back to your initial point. What are the total number of degrees that you just went through? That was a triangle, right? We're in a triangle if you look at it from the outside. 90 plus 90 plus 90, that's 270 degrees. It's a 270-degree triangle. That's what happens to triangles of a certain size on an open structure like a universe. Excuse me, a closed universe, like a sphere. A flat universe, 90 degrees total. 180. Thank you. 180 degrees total. On a open universe, you might get a 90-degree total triangle. You might get 330s to make you a 90, or something like that. So this is testable empirically. What we can do is kind of like shoot stuff kind of way out into space you can imagine, and then on other lines, and you measure how many angles you went through to get there, and if the answer is 180, it's flat. If it's a little more than 180, it's closed. If it's a little less than 180, it's open. all of our measurements that we have done to date, all of them, indicate that we are completely flat, plus or minus 1%. But basically, that's within the margin of error. So basically, we live in a flat universe. If we live in a flat universe, this is not true. That only works in a closed universe. So if you live in a flat universe and the universe is of finite size, like the observable universe that we see right now, and so you live in a flat universe, all the science that we have says that we live in a flat universe, and the universe started some time ago, whether it's 6,000 years ago Earth time, or whether it's 14 billion years ago Earth time, or whether it's 1,000 million billion years ago. It is a finite size because you can't expand, no matter what rate you expand space, you can't expand it to infinite in a finite period of time. So if the universe is a finite period old and the space is actually flat, which is what it tests to be, then that means there is a center to the universe. Now, modern science does not like to deal with this because it sounds a little bit too Copernicus kind of stuff for us. But at the end of the day, that's where the evidence leads us right now. I just point that out to say, we still teach in the textbooks this thing right here, even though we know, according to the best science that we have today, that that ain't true. But we still teach it. Why do we still teach it? The answer is people don't want to deal with the other models.
I was just going to ask, so if the closed theory is incorrect and we do live on a flat plane, how do Big Bang theories account for the fact that that would be a single level of spread, essentially, as opposed to a spherical spread?
Yes. So to answer that question, let's go all the way back to the assumption that started all of this. This was back in the day when we thought the universe was the size of what we think the galaxy is the size of now, like that our galaxy was it. And Hubble builds his big telescope and he looks out and he's like, wow, those don't, everything's moving away from us. Why is everything redshifted? Why is everything, the further stuff away further things are away, it seems to me the faster they are retreating. Now, there are only two regimes in which that occurs that we can think of. One of them, he says, is too horrible to contemplate. He doesn't even mention what it is. And then he says the second one is that the universe looks the same from every point. And when you go through a astronomy class nowadays, you'll hear this said. The universe looks the same from every point. And what they mean is stuff that's close to you will be a certain amount redshifted. Stuff that's further than away will be more redshifted, and they'll call this Z in these books, the Z factor. And stuff that's really, really, really far away from you will be really, really, really redshifted, i.e. the sound of the ambulance siren is really, really low pitched. And so that's the model that they're using. What Hubble was talking about, the thing that was too horrible to contemplate, is that we're at the center of the universe, or our galaxy is at the center of the universe. So these effects don't occur within the galaxy. Because the expansion of space is so slight compared to the forces within this gravitational potential that we exist in that basically the effects are zero or negligible in something like our galaxy. But once you get outside the galaxy, you would see these effects according to the way the theory works. So to answer your question, in a flat universe, if you pin the guy down or the gal down, they're going to be like, well, if flat, yes. If flat, if finite, and we see what we see, then we're at the center of the universe, or our galaxy would be at the center of the universe. Or we'll say, maybe better to say near the center of the universe. Maybe it would be hard, based on the data, to say whether it's us or Andromeda or something like that. That's really the center. But we can talk about, like the local galaxies, we seem to be more gravitationally bound with than the expansion of space is. So our forces are more important than expansion forces would be, that kind of thing. Did that answer your question? Ish? Close enough?
Close enough.
Okay. Well, if you want to re-engage, this is the class of re-engagement. Feel free anytime.
So what you're saying is, they were up on scale, you should have a flat universe society.
Yes, except flat, yeah, that's right. Except flat universe here is talking about the curvature of the geometry of space. And when we mean the geometry of space, the flat universe doesn't mean, I know you're joking, but in case anybody didn't understand what Steve was joking about, we're not saying that somehow we live on a tabletop. What we're saying is that the universe itself, the total curvature, the total geometry of the universe is Euclidean, not non-Euclidean. Or we could say what would be better to say is on average across the whole universe, it would be roughly Euclidean. Yes, sir.
So what's more like the theory of relativity, where everything is on a blanket of sorts, and each object placed causes its own local distortions?
Yeah, everything I'm talking about here is only and solely based on a relative. Well, at least I'm talking about it within a regime where general relativity is the theory of gravity that we're using. So everything I'm saying, this is not to say general relativity is wrong. I'm saying if general relativity is right, then, and the universe is flat, then you would be living at the middle of a finite universe. So the stuff you're talking about, like the blanket, you know, or the rubber sheet where stuff dips down, that's why I said on average. So around the sun, space would not be flat. Space would be curved. So I'm talking about on average across the entire universe. Is it on average flat, curved, or open? So great clarification. Thank you.
Two questions, because my mind's simple. So trying to envision this right now.
Yeah.
I can envision the balloon all day long, right? We're
Yes.
inside of a balloon.
Yes.
We're at the center of like one of those balloons at Disneyland.
Yeah.
We're inside of a balloon.
Yeah.
So would we be in a, like, my first question, does this mean we're in a big cube? And then my second question is, what's the counter argument from the balloon side of the house? Why did they form that theory if basically, if what you're saying is evidence flies in the face of it, like where did that originate from? What's the counter argument we're gonna get if we get, into a discussion about this with someone else?
Yes. So the idea would, maybe a couple of ideas here. Let me think of what, I don't know that I'm, can explain this terribly simply without getting into more and more explanations, which probably means I don't understand it well enough. As Richard Feynman said, if you can't explain an idea simply, you don't understand it, no matter how complex the idea is supposed to be. So this is my best shot at it, but it may just indicate I don't understand it very well. It's the case that you can think of rubber, okay? Rubber can be in the form of a balloon, or you can make a rubber sheet. So a closed universe is the balloon geometry. A flat universe, i.e. the one that we test and seems to be the case, is a rubber sheet. So in the same way that that if you're just talking about the rubber sheet, so a balloon, the geometry they're talking about is, here's a balloon, it's spherical, and so, but that's just one plane. So where does the next plane go? Well, it goes smaller in on the radius of the balloon, and the next one might be bigger. And so you imagine basically more like a rubber ball that's all the way through, and you can slice through that. Let this be the X plane and this be the Y plane. The Z plane comes out at you from the balloon, and the balloon itself would have to have more and more layers. Now that's not right, because that takes us back to, you could just say, well, wait a minute, if you do that and you stick this thing all the way out here, isn't it the case that the shortest point between these 2 points is just this line here? Yes, this is why these analogies don't work, because we're taking two-dimensional stuff to talk about three-dimensional stuff. And if you're concerned, you're like, well, that doesn't make sense to me, my mind can't get around it. Hey, the brightest physicists, cosmologists, and mathematicians on the planet will tell you the same thing. They're like, you can't envision this one, our brains just don't do it. However, if we say things like, there can be planes and there can be lines, then what we're saying is we live in 3 dimensions, but we can reduce these in some way to 2 dimensions, and then we can reduce that in some way to 1 dimension. So if you can do that, then they also say, well, then you can also expand into 4 dimensions or 5 dimensions. Now, you can't picture any of that. And the truth of the matter is you can't actually turn things into 2 dimensions either. Because anytime you say, I'm going to make a plane that's completely flat, and there's no depth to it at all, you say there's no depth to it at all, and by the time you logically assail it, it turns out that you can't actually build that construct logically.
It's super thin, but it's still got volume.
It's still got something, because if it eventually has nothing at all, then, or maybe this is better seen in a line with a point. If a point has literally 0 radius to it, if there's no size to it at all, and you ask Leibniz's question, if 2 things have no properties in which they differ, then they're the same thing, they're identical. That's Leibniz's law. So if you say, well, this is a mathematical point. All right, tell me the properties of this point. Well, it's a mathematical point. Yeah, you said that already. That's a name you gave it. What does it mean? What's its size? It doesn't have any size, 0. How much space does it occupy? It doesn't occupy any space. I'm talking about a location in space, but it doesn't occupy any space. Okay? Then you keep asking these questions, and you say, tell me the difference between this mathematical point that you're saying is there and if I said there's nothing there. And at the end of the day, the poor mathematician or logician is stuck, and he's like, there are no properties that this point has other than me saying this is a mathematical construct. In which case you might say back to him, well, that's a fiction that you're making up. And at the end of the day, if you say what is ontically there, what's really, really there, and there's nothing, there's no difference between that and nothing. If there's no difference between that and nothing, it means that it's identical to nothing. If it's identical to nothing, it's the same as saying there's nothing there. Well, if you can't take it doesn't matter how many nothings you add together, you don't get a line out of that. It doesn't matter how many lines of nothings you build, you can't get a plane out of that. It doesn't matter how many planes of nothings you build, you can't get a space out of that. So there's a problem at the absolute foundation of mathematics, of geometry, in that these geometrical you can't construct geometry that way. So you basically, in my opinion, and there are many opinions out there and they don't agree with mine, I'm the minority, you can't, all of this is fictional. And if you start talking about reality, you have to recognize that that means the rules change, not the same rules. But in any case, even in to the question, imagine the rubber sheet. Okay, so what we're saying is I've taken all three dimensions of the universe, I've reduced it to a rubber sheet. If that rubber sheet started out at a certain radius, a certain size, either 0 or let's make it really, really small, and you stretch it out, if you've been stretching it for a finite amount of time, it doesn't matter, it's got an edge. So the other, you can't race it out fast enough so it doesn't still have an edge if it happened a finite period of time ago. So what this actually means as well is not only would we be near the center of the universe based on our observations, it also means the universe has an edge to it. Now, but not like an edge that you walk to and you fall off into waterfalls and turtles or the Bifrost, where it goes off and Loki falls off into wherever he falls off into. Not that kind of edge, but a kind of edge that when you get there, there's nothing at that point. Now you might say to yourself, that's not even logically, what does that mean? In a world where we are, now let's go all the way down to the smallest level and let's make something up. Let's pretend that every atom in the universe, every quark in the universe is actually some sort of wave form, right? All we're saying is there's a place where there's a tied down node at the other end. It just means that there would be structure to space. Which we know, we think there's some sort of structure to space, whether it's quantized or not, or continuous, we don't know. But in either a quantized or a continuous regime, you can still have an edge to space. It just means that if your waveform gets to this edge right here, and you try to push past it, it just matter-wise, it can't happen. And there wouldn't be any light coming from it because there's nothing generating photons from over here. So if you could somehow get your eye to the edge of it, it would just look black. You wouldn't see anything. You could turn around and see the rest of the universe, and you go stick your eye up against the glass, so to speak, and you just don't see anything. And if you try to reach your hand through it, you would be expanding the universe by reaching your hand into it if you could do that. Now, arguably, based on what we see, the edge of this universe is running at the speed of light away from us, so you couldn't make it there anyway. So it depends on what you think about all these theories. It doesn't really matter. Ain't nobody going to get there. Right. That's a good way of looking at it. And all these neat wormhole things, these all depend on a curvature of space to some degree, localized usually, but there has to be curved space for that to work. Yes, sir. This was not intended to be a class in theoretical physics, but you guys did this, not me.
Well, continuing on theoretical physics.
Yes.
So, because earlier you mentioned that essentially if it is true that we're on a flat plane, that everywhere looks the same as everywhere else, it looks like it is the center.
Say that again, because I think you said two things that are actually contradictory.
Sorry. The part where you were talking about how if you, no matter where you go, it always looks like things are expanding away from you at an equal distance.
That's a speculation. That's speculation. So we don't know because we can only see it from one spot. But yeah, let's say that's the case. Theoretically, yes, right.
That means if you were standing, if you managed to make it to one of the edges, it would only look like that.
Yes. So in that here in this kind of flat plane universe I was talking about, let's say you're near the middle. This would mean anywhere that you look, stuff that's further away from you will look like it's moving away faster. Stuff that's closer to you will look like it's moving away more slowly. In a universe like this, if you move over here, that's not the case. This part that's close to the edge, the stuff that you see won't look like it's moving further away from you. And in fact, if the universe is finite in size, there'll be less stuff in that direction. So you look in that direction, you do kind of the Hubble Deep Field, and you're like, huh, I don't see as many galaxies. I turn my telescope around this way, and I'm like, wow, lots of galaxies per unit, per area that I'm looking through. Over here, less. So the universe wouldn't look the same from all places. That it looks the same from all places is an assumption that you're in a closed universe. Yes, no, easy one to make, because at the end of the day, these are all fictions that are bad analogies. So we're trying to use bad analogies to try to understand something.
Yeah, that's what I was going to say. That's what the balloon analogy was
Built to say.
to
Yep.
explain how you could, yeah.
Yeah, that was my second question. So was that developed basically to I mean, because the perception in science that I'm picking up here is, oh my gosh, it's so much hubris to assume that we're at the center of the universe. Surely we couldn't be, because then we'd have to believe in God, right? So was that developed to basically get around?
I don't know that it was a particularly anti.
Was that just a symptom of the explanation?
So this depends on whether you think Christianity, theism, Judaism, whatever, specifies that the Earth or the sun or the solar system or our galaxy is at the center of our universe. So there actually isn't anything in the Bible that says we're at the middle of the universe. So we assumed it, right? And we didn't, we're not the first people to assume it. The defense that the medieval church picked up was the defense typically of Aristotelian thought and Greek thought on philosophy on a lot of the stuff, which was kind of mixed with Christianity at the time. And so you see people, the church basically backs this Ptolemaic system that's out there. And when guys come out and they say, well, I don't think that that's the way it works. It's not crystal spheres, and we're not at the middle of it and all that stuff, Copernicus and whatnot. They say, it's heretical, not because there's a Bible verse that says the sun's the center of the universe, Earth's the center of the universe, and the sun rotates around it. Rather, people interpreted that Scripture was saying something like that. And I don't know anybody nobody, including the Pope, has not turned around and been like, no, we condemn that Copernicus guy. He's wrong. The Earth is the center. The sun goes around it. I think the Pope's pretty happy to say the Earth goes around the sun, relatively speaking.
The other thing to keep in mind too, right?
Although that's not true, right? Everybody knows they actually go around each other based on the way we understand things. And all that goes around a galactic center, and all that's going in some direction. So none of it does these nice little circles. The Earth is doing this corkscrew through space with a wobble to it that the sun and the Earth represent a separate center.
In elementary school are so much easier.
They really are, yeah.
But something else to keep in mind that people forget all the time. Okay, two things. One, all the space exploration, like all the ability to really seriously see into space is only in like the last 100 years, right?
Yes.
So all these things that we're like where you stand depends on where you sit. Like it shouldn't shock people that we are prone to think we're the center of the universe because we can't see the universe from another vantage point. Well, I mean, I guess we can now because we launched.
But not far enough away to be terribly useful, yeah.
Right. And then the other thing is Tim Mackey,
Yep.
the guy who does the Bible Project, he also does Explore My Strange Bible. He makes a good point in there when he's unpacking the first chapter of Genesis. When it talks about earth and heavens, like everyone thinks of the globe, right? Everyone thinks of the earth. That picture's only been around for 60 years.
Right. They're talking about
space exploration before that. So like back when this was written thousands of years ago,
heavens and the earth just meant like everything that there was, yeah.
Right, exactly. Right. Earth was the ground and heaven was the sky. It wasn't like earth, like this ball.
Right.
We think of it like that now.
So, and maybe I think I got offline answering the original question, but yes to this. But was this a reaction to theistic thinking? No, it was not. It was observational, and it was the case that everybody thought Copernicus thing is dead. The Earth is not the center of the solar system, and if not the center of the solar system, then why would it be the center of the universe, right? Maybe that was the thinking. And so we keep bumping into Copernicus though occasionally. So the measurement of the universe that the space is flat, this bumps us back towards Copernicus a little bit, if not to say the Earth is the middle. Here's something that was really wacky. We sent out a probe a few years ago, maybe 10 years ago now, I forget how long ago, a while ago now, called the Williamson-Michelson anisotropy probe. And the idea was we're looking, we did this look at the universe. We see everything moving away from us at some speed, and then somebody does the math and they're like, hang on a second, if everything moves away at the same speed, then Big Bang doesn't work. There has to be some inconsistencies. And then somebody else does some other math and is like, well, if the inconsistencies are too big or they happen too early, then the universe never expands and it goes and wraps around itself and kills itself. These are very rough, inaccurate statements. But basically, there's this like super knife edge balance at which things have to happen on this expansion, or it never gets past the golf ball size of the universe. It recollapses in on itself or it tears itself apart. So there has to be some super specific distribution of matter and energy and heat and all that stuff. And before there was matter, of energy and heat and what we might call heat now, of the stuff of the universe. And so they expect now to see, they're like, okay, rats, well, even at the quantum level, this is what it should look like. But they expected to see, when you look back into it, and you look at the night sky, the dark part of the night sky, if they're the darkest part of the night sky, you still see this, what they call microwave background radiation. It's in fact responsible for like 3% of the static on your TV, back for those that remember what that looked like. 3% of that was microwave background radiation. They used to think it was a problem with pigeon droppings on their antenna, the first guys that did this. And they cleaned it off and they're like, it's still there. More pigeons? Turns out it's everywhere. And so this 2.7 degree Kelvin radiation that's coming from all of space, now we believe is the remnants of part of the Big Bang, or that's what modern science in total puts it down to. And they said, okay, and it's even everywhere. And then someone was like, ooh, even everywhere means no Big Bang. And they're like, well, that's not right. Let's refine it and figure out what it is. So they put up a better probe, a better set of probes. And one of the most recent better sets of probes was this WMAP satellite. And its job was to look for very slight temperature differences in this 2.7 degree otherwise uniform radiation, because if you didn't have those temperature differences, would be the seeds of the galaxies we see today, something like that, and the stars and all that. When they did that, they do this analysis that includes something called an octopole analysis, eight different poles and directions, and it turns out that the universe is anisotropic. That is to say, it does have little temperature differences depending on where you look, but there's a generally warmer difference above us and a colder difference below us, aligned with, get this, the ecliptic plane of the Earth. Now, here's the weird stuff. Like, this should be random, right? So here's the plane in which the Earth is going around the sun. And so you would say, let's say there's a temperature difference between two parts of the universe, just generally on average. What's the probability that it's lined up exactly with this plane? And you can run the numbers on that one. So you can imagine if you just took kind of like took your protractor and you said, all right, well, if we call it in degrees and we say we're as good as 1 degree, then there's a 1 in 180 degree chance, or maybe you count these as the same. Maybe you just want to say there's a 1 in 90 degree chance that there would be a difference, 1 in 90. And then you do it in the other direction, and then you combine these and you run the math on it. It's not highly probable that you would end up with it just happening to line up with the eclipse. That's a highly improbable event. And yet that's what it is. And so famous atheistic, rabidly anti-theistic physicist Lawrence Krauss I've got a great quote from him, I'll find it sometime, says, and here's what this is. He goes, this is crazy. Is this Copernicus coming back to us again? I mean, we can't make any sense of this. And so what does this mean? And he just runs past the question and says, okay, that's just the way that's the way the universe is. Sometimes it's weird. I'm not saying you should say, well, there's something to do with the ecliptic plane of the Earth around the sun, therefore some biblical geocentric model of the universe is true. That doesn't follow. But it is highly improbable, and it's something that you have to account for, probably with something better explanatorily than, we just got really lucky. Because right now the number of, we just got really lucky when it comes to do with this universe, there's an awful lot to it.
But that model wasn't in response to a theistic worldview.
Yeah.
And there's no tenet in Christianity or Judaism that requires that the Earth be the center.
Yes.
Why is that a major problem?
I don't think it is a problem.
Okay.
Yeah. I don't think it is a problem. I think the reason to question whether the universe is this or this has nothing to do theologically with anything. To me, this is a scientific question.
And you keep saying it's a whatever fate that can't be found, whatever the quote was.
From Hubble.
Yeah.
something too horrible to contemplate. No, you know what? You're right. I think that when Hubble said that, he is thinking a little bit of like, this would make us special. This would put us in a special place in the universe. And if we're in a special place in the universe, so to speak, if we happen to find ourselves at a special place in the universe, then you have to ask yourself two questions. One, why is the question, but are we at a special place in the universe? Is the why explanation because, well, in universes like this, as it turns out, because of the way the forces work, the only place that something like the Earth can form would be at this locus for these physical reasons? Or is it the case that there's a God behind it and he's like, I put you in a special place because you're special, right? So our initial way of looking at business would probably want to say, if it turns out we're in a 1 to the 10 to the 10 to the 120th power kind of probability space, maybe that seems to be evidence that we are special in some way. Why are we special? And a God hypothesis is an explanation of why we're special. If you can get rid of that specialness, then you don't have to debate the why. You can just say that's not the way that it is. So I think, now this is in the psychology and I have no right to speculate on why people do what they do, but at least one explanation of why psychologically you would prefer this model to this model would be if this model makes you have to deal with a God question, scientifically speaking, and this one doesn't. That is to say, this provides scientific evidence for a philosophical statement or metaphysical statement, God created all of this. On this regime right here, you don't really have to, on that particular thing, there's nothing to debate. On this one, all of a sudden the theists have got hey, we're in a special spot. Non-theist, what's your explanation for this scientific data that shows that we're in a special spot? Yes, sir. And what we mean by this is,
or is that moving? Because if it's moving, then is there a
right.
possibility that they just measured it at the time that,
right.
that it was in line?
So here,
like the argument that I just would.
I forget the. So the answer to your question is, this is a question basically of inertia and momentum. So precession is going to come in. Gosh, this is not what you guys came here for.
It's just the only thing that I could say. That would be a quick answer.
Here's the center of the galaxy right here, okay? So here we are, we're on the western spiral arm of the galaxy. That's the western spiral arm of the galaxy, we're way out here. And so we're moving, basically the sun's moving in this direction. We're going around the sun like this, but we're also moving in this direction. So when I said we're doing a corkscrew, you'll see what I meant was we're basically, doing this as the sun moves in this direction around the galaxy. Now, as we move around the galaxy, so here's I forget the angle that we're at, but let's just call it this angle. As we move around the galaxy, do we rotate this way with the galaxy, or are we kind of based on the inertia that we have, like a gyroscope, us going around the galaxy itself? Do we, like a gyroscope keeps its position, even when you do this to it, kind of on a string? The Earth keeps its position relative to the sun, roughly like that. Now, you will get precession effects, but it ain't nothing we're going to be able to detect, at least to my knowledge, with the level of instrumentation that we have now over the time periods that we have now. So should it change a little bit?
So relative to
Maybe.
It's going to remain.
It's going to, at least for over the lifetime of humans, even if that happens to be, millions of years, it wouldn't change hardly anything at all. Like, be really difficult to measure that level of change, as I understand it, assuming I get it right.
The stars should all be womping around in the sky rather than just.
Now, it is the case, like if our understanding of the universe is right, the North Star that we have right now was not Polaris, was not the North Star 50,000 years ago, if the universe is more than 50,000 years old. Another star would be it, and in another 50,000 years, the North Star won't be exactly north to us anymore. But that's from a whole combination of effects. It's not one single effect that does that.
On a rubber sheet with the two dots, would there be other observational differences besides the concentration of stellar bodies?
Yes, yes. The speed of the ones, you would see differences in speed from observable. Let's say that in a weird universe, for some reason, you kind of end up stuck because, as it turns out, there's as many dots over here as there are over here, and that's a function that the universe just kind of was made that way. So this is a trick, right? How do we figure out that we're not at the middle of the universe? How do we figure out we're at the end? Well, as it turns out, these redshifts right here, the z factor for this one and this one and this one, would be much less than this one, this one, and this one. So basically whatever the absolute, so to speak, difference is between these positions should be reflected in a redshift. And so let's call that a 1, let's call this a 2, let's call this a 3, let's call this a 3, a 6, and a 9. You'd be able to look either way and be like, I measure 3, 6, and 9 direction, I measure 1, 2, and 3 in that direction, even though there's the same number of galaxies on both sides. We're way more redshifted over here than they are over here. Why is that? And one of the explanations would be you're probably on closer to the edge of one of these sheets.
Okay, so to clarify, you're saying that it is the case that even if we were closer to the edge, there would be equal concentration?
No, I'm saying in a weird universe where that happened to be the case. An assumption you might make is if you're close to the edge, there should be less galaxies here than there would be here. And that's an assumption of homogeneity, which is to say that it's homogeneous, that the amount that the number of galaxies per unit area is roughly the same.
Okay, so in this case, if to the left, when we reach the edge of the universe, the maximum redshift is 3. If we go to the right 3 units, also the maximum redshift we would observe would be 3.
No, it would be 12 or something out here.
Well, I'm saying that if we don't look further than that 3.
Oh, this 3 distance, yeah. If all you did was look this far, you would say, yep, well, we're in the middle of the universe, because you're in the middle of that part of the universe.
Okay, so even if there was an edge, if our observable universe was to the distance of 3, it would still look as though we were in an infinite universe with everything being homogeneous in distribution and speed.
Say that again.
So if you drew an observable universe bubble in this case, even with a universe that actually had an edge, observationally it would still look homogeneous in every direction?
If you couldn't look past this right here, yes. So how would you determine the difference between these two? No, that's not true. Because what would happen is you would have an absolute movement from here to here, from here off in this direction. So you would be moving in this direction faster than these parts right here would be moving in your direction. So it should not look the same. You would be kind of, quote unquote, you wouldn't be catching up with these over time, but you would be leaving these faster. So that stuff that would be towards the actual absolute center of the universe would be running away from you, these redshifts would be increasing over time compared to these redshifts.
That last part I don't understand.
So think about this sheet. Now I've really gouged it up, haven't I? Here's your sheet again, and you say, here's the middle of it, and you say, how much is it stretching? And the answer is this much stretched, this point stretched that much, but this point stretched that much, but this point stretched that much, and now I've kind of got myself to the end of it. And you do some more of these, and basically this becomes the geometry of your space here. So even though this looks like a plane, the amount that space has been stretched, the amount that the actual physical geometry has been stretched, is less here than it is here, than it is here. So that's how much, this isn't done terribly well, but think about it just in this direction. So if you find yourself out right here, this is where you happen to be. Something that was, back when you were at, let's say that's midpoint between those two circles, right here, as your point got stretched all the way out over to here, this part right here got stretched a certain amount, and this part right here got stretched a certain amount. Are those amounts the same? The answer is as far as we know, would be no. You would expect to see greater, or let's say yes, let's say it stretched uniformly everywhere. You would expect to see more stretching effects relative to per unit space than you would in this direction. I don't know if that was clear. That may not have been clear. But in short, you should be able to see the difference when you look back towards the center from which you were expanding.
That runs counter to what I percentage increase was thought to be equivalent.
It is, yeah, that's the idea behind it. So, but remember, there's also, so go back to this place. Maybe I'm not understanding your question. Your question is, here we are right here. Can you look here, here, and here and say that there's a difference between here, here, and here? Is that your question?
I couldn't quite see what you're
Here, let's say this one and this one. You're trying to say, can I look in either one of these directions? And looking at this and looking at this, would I be able to tell a difference? Yeah, I think the answer to that is probably not. If the expansion of space is identical between any two originally identically spaced points. Now, what you should be able to do, I guess I would ask this question. I drew this circle here in response to you talking about the observable universe. Do you have any reason for believing that that would be the observable universe? So what should be observable, what the observable universe, to my understanding, would look like in this case, you should see a ellipse or an oblate sphere.
Why?
Because this expansion right here from a geographic center here continues in this direction relative to this. And although there's because there is an initial vector that you have as you're moving out. And so subtractions off of this vector, additions to this vector, think kind of Galilean relativity at this point, where like you can be on a car and throw a baseball forward. If you're going 20 miles an hour, that baseball is now moving 40 miles an hour. If you're going 20 miles an hour, this one stops and drops to the ground. So you should be able to kind of quote unquote throw your baseball and see, did it drop to the ground relative to the expansion of space, or did it increase relative to the expansion of space to where I am? And that's assuming you've got this absolute that you can look at. Well, where's the absolute you can look at? If you started out here, then light from here would have reached you, right? Unless that expansion is so great that it becomes the edge of the observable universe. So this is now within the observable universe. And so this would be being stretched out. The stuff launching away from you would have basically been less stretched out unless you can add to it additional velocity. So as I understand it, and let me think about it more, I still think you should be able to look back and see an observable universe that would be oblate. Now, you would have to do some tests. It might look to you as though it's the same. So you would have to do some tests to determine, okay, wait a minute, is the standard candle over here redshifted compared to the standard candle over here? And as I understand this, let me think about it for a second. In distances that appear to be, well, one of our problems is when we get out to a certain distance, we can't do kind of parallax stuff. We have to trust on received light and its redshift to determine where we are. So how would you go about doing that? I think, in short, what you would likely see is if you assumed homogeneity, you would see, Brian, basically back to your point, you would see a difference of a greater number in one direction of things in the universe. This is where I think I'm back to my original point. So I think the answer is, yeah, ultimately the answer would be there's more stuff in one direction than there is another direction. And the redshift of the stuff in the other direction would exceed, the furthest things in that direction would exceed the redshift of things in this direction. I think it basically boils down to that.
And if I artificially imposed an observable universe inside of that,
Yes.
you wouldn't know.
Yes, that's right. But why would, you would have to chop off stuff that should be observable to make that the case. Yes, ma'am.
So this may be assigning myself homework that I'm not sure I have time to do. Next class, could we maybe YouTube this stuff? Because the visualization is so incredibly hard. I feel like we're trying to draw the Bohr model of the atom.
Yeah,
and
yeah, yeah.
It's just not quite there. And I know there are videos out there that show the different possible shapes of the universe and the expansion of the universe and cosmic background radiation.
Yeah, I'll go and look. I'll go find some of those and I'll send them out for those that are terribly interested in this one, because I don't, I won't ask for a show of hands, but there's probably some percentage of the class who was like, wow, when are you guys going to be done with this stuff? If you happen to be in that part, no worries. I'll find this stuff and I will send it out. So great, good idea. Yes, Steve, and then
I was going to
Mark.
kind of change the subject a little bit, but I have just a question that underlies all this.
Collective Psi from part of the group. Yeah. So to,
some additional principles in there that I don't fully understand.
to Katie's point, I'll mark a video out that answers that question too. You have probably heard of inflation theory. That was a solution. So one of the problems was when you run the Big Bang and you assume that the expansion of space was the same from the beginning of the Big Bang to the current time now, it doesn't work. You can't get it started, so to speak. So you have to kickstart the Big Bang with an expansion of space that's over 1,000 times faster than the speed of light. Now, you don't have to do that very far, because I forget the size in which that expansion happens, but it's tiny. It's in the first, fractions of a second. But basically, you have to jumpstart the universe, and then you can make it do this. And so, the kind of problem with this theory is that there's exactly zero evidence for it. But the rest of the theory doesn't work unless you do that. So it has become, the guy who invented that is Alan Guth. That theory is his. He's up at MIT, and you can see Guth's lectures. There's MIT OpenCourseware has Guth lecturing on this, both in a fairly rigorously and impenetrably difficult mathematical system, and then I think he's got one or two on that are a little more popular that you might watch it and be like, I didn't get all of that. He got into the math stuff and I missed it, but at the end of the day, I got what he was after because he fills in with enough English to understand what he's talking about. But basically, if you ask the folks responsible for thinking through this stuff, they will say, yeah, right now we don't have any particular verification that that's true, but we do know that if the Big Bang model is true, then something like that had to have happened, or we wouldn't see what we had. So a little bit circular on the reasoning there, but ultimately, in short, the answer is what's the speed of the expansion of space? It's assumed to be constant, except for the initial inflationary epoch, and that now there's some folks who say, most of science, astrophysics says, and cosmologists say, the measurements that we're getting right now indicate that it's possible that if our theories of dark matter and dark energy are something like close to correct, even close to correct, then it looks like the universe is increasing in the rate of its expansion now. All of this is in response to something we've been trying to solve since Einstein's published his general theory of relativity. Just so, don't get blinded by the science. The general theory of relativity is simply a model of gravity. How does the gravity in the universe work? It doesn't explain anything else except for gravity. General theory of relativity is only about gravity. And the rest of quantum stuff has to do with all the other forces. The other three forces are depending on where you unify them. So there's only one force that we're talking about here, and that's gravity. And that means that, like, if you have a theory of gravity and you have a certain amount of stuff, billiard balls that you stick in space, your theory of gravity should tell you what happens to those billiard balls. And at the end of the day, if you stick a bunch of billiard balls out there and they're not moving and you let them go, gravity, if there's a theory of gravity and there's nothing else out there, they are attracting each other, right? So there's attractive force, so all the billiard balls fall in together and they collapse. So the only way to get all the billiard balls to not collapse on each other is to give them a little bit of a kick in every direction. And you have to kick each one of them a certain precise amount so that they go and then they just kind of hang there, because there's this exact balance between the kick they had and the amount of gravity that's pulling them together. So it's either the case that there's a drift and it just drifts apart and comes apart, that the kick wasn't big enough and so it collapses again, or you kicked everything exactly perfectly and it gets to one point and it's just balances. Only if space is curved a certain way does it work the way that I'm describing right now. And Einstein was trying to do that. He wanted to kick each one of these balls and balance them on a knife edge. And someone pointed out that, like, basically if you blink in one direction, it wrecks all that. And so all of it, and now you get all kinds of messes. And so Einstein, in order to make this happen, had to put a positive, because he realized there's no way to balance it on that edge. There isn't really an edge between it continues to expand and it eventually collapses, unless you stick a positive pressure in there, something that pushes the billiard balls apart. And that's what he called the cosmological constant. And then people came back and criticized it for being an extremely stupid idea for such a bright guy, and he called it the biggest mistake of his career. And then 50 years went by or something like that, and then we were like, hang on, maybe it wasn't such a dumb idea after all. Maybe this expansion of space is that positive pressure. So this stuff that you hear called like zero-point energy or dark energy or any of that stuff, that's that positive pressure that he used in his equations. It's just this constant. It's literally a fudge factor that Einstein crams into the math that comes out of the geometry equations that helped him build general relativity. And he crams this thing in there to balance it. And now we think that there's something like dark energy that does that. All of this, if this field's a little bit loosey-goosey to you, and like we've been changing it a lot over the last 100 years, that's exactly true. So don't let anybody tell you, like, we got this figured out, dark energy. What is dark energy? I don't know. What do you mean you don't know? I think it's this lambda thing, but maybe not. Could be something else. Thor, what is it? Oh, the dark elves brought it to us. It's some sort of red thing. Thank you, Thor. You know, it's this, there's a level of crazy here that we are talking about. So I saw and something in the, one of my favorite satirical things that pops off on Facebook is the Babylon Bee. You guys seen this one? It's like the Onion for Christians. And it said, atheists believes in an infinite multiverse of all possible universes except for a universe that includes God. And so it was kind of a funny, take on it. But in any case, there was an original question I was answering. The rate of inflation is under debate, and whether it's constant is under debate.
It seems like it would violate our understanding of the speed of light.
Light is. So that speed of light thing has to do with basically photon movement in a given geometry. If you stretch the geometry out really fast in one place and you don't in another, it just means that if you can see those light signals, you should see some effect of that. In fact, LIGO uses that to detect gravitational waves. That's the theory behind it. But yeah, it doesn't technically violate an axiom of relativity, which is the light moves at a certain speed in two directions. It moves the same speed in that direction as it does in this direction, and that there's a fixed speed of light. That there's an assumption stated in there that says basically for a given geometry. We don't say that because if we qualified every scientific statement mathematically, they'd all be miles long.
So do they have an idea where the center of the universe is today? I mean,
Yeah.
so, so this is us, right?
It depends.
Well,
It depends on your model. If this model, if the universe is flat, we are somewhere around here, yes. Based on what we can observe, we should conclude that we're somewhere around there. That's what Hubble was saying.
this being then the center, because everything's expanding
Yeah,
out from it.
that's right. Now, we're at like the precise point center. Where is that? Is that the middle of the galaxy? Is that the sun? Is it the Earth? And the rest of the,
Because I was thinking if we were somewhere out here, then, stuff out here is red shifting more than the stuff behind it, but it'll still be red shifting because we're moving away. But something moving parallel to us wouldn't be red shifted because we're moving parallel.
yeah, that's right. And we do see stuff like that, like the Andromeda galaxy is headed in our direction.
Okay.
Yeah.
Wait, but aren't we moving away from it?
So this is where I'm saying gravitational effects. Sometimes you might stretch out in your rubber sheet. You might stretch out parts of the rubber sheet, but you've got the two balls sitting in the rubber sheet. Have you seen that one where they, like he was referring to, they sink in? Well, there's a distance where the two balls that are kind of bent into the rubber sheet. It doesn't matter that the rubber is being pulled apart. They're now caught in each other's gravitational pull, and they're coming together. You can't pull that rubber apart fast enough. And so Andromeda and us are too close together for the rubber to pull us apart.
Okay, because I was thinking if we were out here somewhere, there could be a whole another universe that's moving out this way at the speed of light that we can't see because it's moving out that way.
Yeah, when we speak of the universe, at least in this context, we mean all that there is that's connected causally.
So if we're close to the center, then we're seeing everything shifting away at about the same.
Yeah, you look in that direction, and the greatest redshift you see is z equals something. And you look in that direction, and it's the same. And you look in that direction, and it's the same. You look in that direction, it's the same. To Brian's question, the observable universe, if we're at the edge, should be a redshift there is 0.5 max. This one, it's 0.9 max or 7 max or something like that. Those are the measurements you should make that would tell you where you were relative to the center. Yes, ma'am. Now, we're over time. If you need to walk out, please walk out.
Is this a fairly new observation? Because granted, my knowledge is 10 years dated from back in college, but I was always taught that cosmology generally described an infinite universe.
Yeah, so
is this because we've now decided the universe is flat? Is this...
That depends on what you mean by infinite, which is another thing that I've got a bone to pick with. in an infinite universe like this, the globe, in some ways, you can say is infinite, because you're going to say you can come back to the same point, but there's not an end to it, there's not an edge to it. So now someone might say, well, that's needlessly pedantic, that's not true. If you can come back to the same point. But that is what they mean by infinite. There's not an edge to it. So in that regime, infinite doesn't, in my opinion, mean infinite. And secondly, well, at any rate, yeah. Or what you might say is this: how long does it take me to walk to the end of the earth? Forever. Okay, so that's what they would mean by infinite in that regime. Now, what you might say is, if I left one point on Earth and I walked a certain direction, I would come around the maximum extent of the size of the Earth, the largest distance that I could walk. In that case, was, however many, I forget, 12, whatever, however many kilometers the Earth is around. And I would now have come back to the same point. So there are some people who say, if the universe is closed and a certain amount of stuff, then you should be able to look through a telescope in a particular direction and see the back of your own head. That would be an example of that one. The universe is expanding so fast you can never do that. Depending on, you just can't do that. The curvature would not be great enough. But in the sheet version right here, what some of these guys are basically assuming is there's no reason, like, why should we say the sheet? And I'm drawing a rectangular sheet. The sheet would be circular. So the circular sheet, mathematically, there's no end to the plane. So space should go on in all directions. And so maybe the reason that we only see a universe of radius 96 billion light years is because that's all the time that we've had. But maybe the universe is bigger than that, and we just can't see back out to that size. So we want to speculate that the universe could be infinite in size, even in a flat configuration. Now the problem with that is that just makes Big Bang not what we would think of it as the creation at the beginning point of the universe. Yeah, we're basically back to Newton. Is there an infinite void and time span on which we're running, or is all this finite? And this is why Craig got all excited about Borg-Bluth-Vilenkin theorem, because when you run all this stuff backwards, it makes a real deal beginning point. So I just want to point out that the assumption out there that you're being taught in school that this is all infinite is exactly that. It's an assumption. There's no empirical evidence to support that. It is a philosophical position that says when you use mathematics and you're working with a plane, that plane is infinite. Thank you all very much for your time and your contributions. In case you want another class in theoretical physics, come on back next time and we'll do our best to answer it. Brian, if I didn't...
Cause you said so.